Hello everyone, in this video we're going to be picking up where we left off in section 10.5, which is finding the arc length in polar form. Right? So remember the arc length in the rectangular form was S equals the area from A to B of 1 plus the derivative squared underneath the square root. So that was our formula for the rectangular coordinate system. So now what about when we have stuff in terms of polar curves? We're still able to do that, but our formula looks a little bit different. Not too much different though. It's still got the square root. We're still squaring stuff. But here is the formula. Theorem 10.14. So let f be a continuous function whose derivative is continuous on the interval from alpha to on the interval where theta lies between alpha and beta, then the length of the graph r equals f of theta from theta equals alpha to theta equals beta is, and it looks like the function squared, or the radius squared, because the radius is the function, times the derivative squared. Right? So in other words, we take r squared because r is equal to f of theta, or the function, and then we take the derivative of the radius squared. So that is our formula. Right, so again, kind of similar because it's got derivatives and stuff in it, but not exactly the same. Right, so this video actually should be pretty short because this is our last example. Okay, so example 3. Find the length of the arc from theta equals 0 to theta equals 2 pi for the cardioid that's r equals f of theta, our function of theta, which is 2 minus 2 cosine of theta. All right, so this is a cardioid. It tells us our alpha and our beta, right? So really it's just a matter of plugging things in and solving, right? So what we need is we need f of theta, which we know that, and we need f prime of theta. So we need the derivative. So f prime of theta, or the derivative of this function, the derivative of 2 is 0, and the derivative of cosine is negative sine, so this ends up being 2 sine of theta. Okay, so the arc length S is equal to the integral from alpha to beta. We're starting at theta equals 0 and going to 2 pi, and then we do the function squared, right? So I do 2 minus 2 cosine of theta squared plus now the derivative squared, which is 2 sine of theta squared, all underneath the square root d theta. So in order to solve this, we're obviously going to have to do some algebra here. So 0 to 2 pi. Let's square this out. So I get 4 minus 8 cosine of theta plus 4 cosine squared theta plus 4 sine squared theta when I multiply all that out, d theta. So notice that I can pull a 4 out of each term. That's going to be pretty helpful for us. So the integral from 0 to 2 pi of 4 times 1 minus 2 cosine of theta plus cosine squared theta plus sine squared theta, all underneath the square root d theta. So the first thing we notice is the square root of 4 is 2. So I can factor that 2 out of there and get rid of the square root of 4. So 0 to 2 pi. The other thing we notice here is that this is sine squared plus cosine squared, right? Sine squared plus cosine is equal to 1, right? As long as the argument's the same. This case is theta. So when I go to do my constant term, it's just going to be 1 plus 1, or 2, right? So I get 2 minus 2 cosine of theta is all that remains underneath the square root d theta. Now what occurs in both terms? A 2 occurs in both terms, so let's factor that out. So I get 2, 1 minus cosine of theta times, or underneath the square root. And now I look at this, and I can obviously pull out a radical 2, but how can I simplify this to make life easier, right? I have a square root. So it'd be really cool if I could rewrite what's underneath here as something squared. And in fact, we can by the power reducing formula. So in the case of cosine, remember it's cosine squared u equals to 1/2 plus 1/2 cosine of 2u. In this case, we don't have 1/2 cosine and any 1/2s or anything, but if I multiply everything by 2, I can get 2 cosine squared of u is equal to 1 plus, and did I screw up a sign? Oh yeah, because I don't want to do this one. I wanted to do sine. Probably should have looked at that. All right, I could rewrite sine squared theta. Why am I choosing sine instead of cosine? Because the cosine one had a plus, and I wanted a minus because of this minus sign right there. Right, so I should have chose minus. In this case, I'll get this formula. So this is the one we want, the power reducing formula for sine. Right, so if I do that now, if I multiply by 2, I get 2 sine squared of u is equal to 1 minus cosine of 2u. Right, so this right here is what's going on right there. And the only thing we have to be careful of now is I need, in order to get from here to here, I need to divide the argument by 2. Right? Normally we're going from there to there because we're reducing a squared to a regular cosine, but this time we're going the other way. So instead of multiplying my argument by 2, I need to divide it by 2. Right? So what this ends up looking like is 2 times radical 2, because I'm pulling out that radical 2, the square root of 2 there. The integral from 0 to 2 pi of 2 sine squared of, now instead of theta, it's going to be theta divided by 2 underneath the square root d theta. So let me try to scoot this over just a little bit so we're not on top of it here. So then, once again, I can pull out a square root of 2. Right, square root of 2, square root of 2. And what am I left with? If I pulled out a square root of 2, I'm left with sine squared of theta over 2 underneath the square root. So the square roots cancel out with each other, and I'm left with just sine of theta over 2 d theta. Right? So now, what is radical 2 times radical 2 is just 2. So 2 times 2 is 4 is my constant out front. 0 to 2 pi. And I can integrate this. I don't need to write it. So when I integrate this, remember the antiderivative of sine is negative cosine. And then remember that I am going to normal. So this is really like 1/2 theta. So when I did this, I normally would divide by 1/2 because that's the constant when I take the antiderivative. So instead of dividing by 1/2, I'm going to multiply by 2, and then I get the cosine of theta over 2. Right, again, because if that was like 2 theta, then I would divide by 2, but since it's already dividing by 2, dividing by dividing is multiplying. Right, so 0 to 2 pi, and then now I just multiply this out. So 4 minus 2 cosine of, that's just going to be pi, and then plus, because minus minus, cosine of 0. So I end up getting 4. Cosine at pi is -1, so -1 times -2 gives me +2. Cosine at 0 is 1, so that gives me +1 multiplied times 2. So this is 4 times 4, which is 16 as my final answer there. Right? So that is how we find the arc length in polar form. Just like when we did arc lengths in rectangular form, a lot of the hard work just comes in the algebra to get things to simplify with that square root to make an integral that you know how to do. Right? That's all I have for this video. Thank you.